When dealing with static charge buildup in pipelines, particularly with non-conductive fluids like oil, ensuring proper grounding is crucial for safety. Several factors influence the required grounding impedance, including the type of static charge, its magnitude and duration, and the area of the grounded object. Consulting relevant standards and recommendations is essential for designing an effective grounding system. Firstly, the type of static charge plays a significant role. Whether it's triboelectric generation, where charge is created by friction, or electrostatic induction, where a charged object influences another, the nature of the charge affects grounding requirements. Secondly, the magnitude of the charge directly impacts the grounding impedance needed. High charges necessitate lowered impedance to facilitate rapid dissipation. Thirdly, the duration of the charge is a factor. Charges expected to persist longer require lower grounding impedance for continuous dissipation. Fourthly, the area of the grounded object matters. Larger areas require lower impedance to prevent charge accumulation. As a general rule, the grounding impedance should be as low as practically achievable to ensure effective static charge dissipation. A grounding impedance of less than 10 ohms is typically recommended for most applications. However, specific standards offer more precise guidance. NFPA 77, Recommended Practice on Static Electricity, provides recommendations for managing static electricity hazards. Section 10.12 of NFPA 77 states that the resistance of the grounding system shall not exceed 10 ohms. API RP 2003, Protection Against Ignitions Arising Out of Static, Lightning, and Stray Currents, offers guidance specific to the petroleum and petrochemical industries. Section 4.3.2.2 of API RP 2003 states that the resistance of the grounding system shall not exceed 1 ohm. It is important to note that these are recommendations, and a qualified electrical engineer should determine the specific requirements for grounding impedance based on a thorough risk assessment of the application. When designing a grounding system, several additional considerations come into play. Firstly, the type of grounding electrode significantly influences grounding impedance. Common electrode types include beared rods, plates, and meshes. The choice of electrode and its installation method directly affect the grounding impedance achieved. Secondly, soil conditions are a critical factor. Soil resistivity, which measures how well the soil conducts electricity, varies depending on soil composition. Sandy or rocky soils typically exhibit higher resistivity than clay or loam soils, requiring adjustments to the grounding system design. Measures to reduce soil resistivity include using multiple ground rods, chemical ground rods, or ground-enhancing compounds. Thirdly, the grounding wire must be sized appropriately to handle the expected current and adequately protected from physical damage. The size of the grounding wire is determined by the anticipated fault current and the length of the wire run. Using a wire gauge that is too small can result in overheating and potentially a fire hazard. It is important to use an appropriate size. Additional factors to consider include bonding, which involves connecting different metallic parts of the system to ensure they are at the same electrical potential. This reduces the risk of sparks and electrical shock. The grounding system should be regularly inspected and tested to ensure its continued effectiveness. Regular inspections can identify potential problems such as corrosion, loose connections, and damaged grounding wires. Testing the grounding impedance verifies that it remains within acceptable limits. To summarize, addressing static charge buildup in pipelines requires careful attention to grounding system design. Consulting relevant standards such as NFPA 77 and API RP 2003 is essential. The required grounding impedance depends on the type, magnitude, and duration of the static charge, as well as the area of the grounded object. Additional considerations include the type of grounding electrode, soil conditions, and grounding wire size. Regular inspection and testing are crucial for maintaining the effectiveness of the grounding system. Proper grounding minimizes the risk of arcing and potential ignition hazards associated with static charge buildup. The selection of the correct grounding method and materials can prevent potential disasters. Grounding systems also protect equipment from damage caused by voltage spikes and surges. Proper grounding helps to stabilize voltage levels. Electrical codes provide specific guidelines for grounding systems. Complying with these codes ensures a safe and effective electrical system. Grounding is a critical component of electrical safety. Ignoring grounding requirements can have serious consequences. A well-designed grounding system can also improve the reliability of electrical equipment. Proper grounding minimizes the risk of electrical noise and interference. Grounding is an essential aspect of electrical engineering. A thorough understanding of grounding principles is essential for any electrical professional. Grounding systems should be designed and installed by qualified personnel. Improperly installed grounding systems can be ineffective or even dangerous. Regular maintenance of grounding systems is essential for continued safety. Grounding systems should be inspected and tested on a regular basis. Any problems with the grounding system should be corrected immediately. Grounding is a fundamental concept in electrical safety. It is important to understand the principles of grounding to protect yourself and others from electrical hazards. Electrical safety is everyone's responsibility. By following safe electrical practices, we can all help to prevent electrical accidents. Grounding is a critical aspect of electrical safety in industrial environments. Industries that handle flammable materials are particularly vulnerable to static electricity hazards. Proper grounding can prevent static electricity from causing fires or explosions. Grounding is also important for protecting electronic equipment from damage. Static electricity can damage sensitive electronic components. Grounding provides a path for static electricity to safely discharge. Grounding is an essential part of any comprehensive electrical safety program. A comprehensive electrical safety program should include training, procedures, and equipment. Grounding is a critical element of electrical safety in residential settings as well. Grounding helps to protect against electrical shock in the event of a fault. Grounding also helps to prevent damage to appliances and electronics. Grounding is an essential component of a safe home. Grounding systems should be inspected and tested by a qualified electrician. Grounding is a complex topic, but it is important to understand the basics. By understanding the principles of grounding, you can help to protect yourself and others from electrical hazards. Always consult with a qualified electrician for any electrical work. Electricity is a powerful force that should be treated with respect. By following safe electrical practices, we can all help to prevent electrical accident. The NEC, or National Electrical Code, provides comprehensive guidelines for grounding systems. Following the NEC ensures a safe and effective electrical system. Grounding is an important part of the NEC. The NEC covers all aspects of grounding, including the size of grounding wires, the type of grounding electrodes, and the location of grounding connections. The NEC is updated every 3 years to reflect changes in technology and safety standards. It is important to stay up to date on the latest edition of the NEC. Grounding is an essential aspect of electrical design. Electrical engineers must have a thorough understanding of grounding principles. Grounding is also important for electrical contractors. Electrical contractors must follow the NEC when installing grounding systems. Grounding is a critical component of electrical safety training. Electrical workers must be trained in the proper procedures for grounding electrical equipment. Grounding is a responsibility that should be taken seriously. By following safe grounding practices, we can all help to prevent electrical accidents. Grounding is a continuous process. Grounding systems should be regularly inspected and maintained. Any problems with the grounding system should be corrected immediately. Grounding is an investment in electrical safety. A well-designed and maintained grounding system can save lives and prevent property damage. Static electricity can be a significant hazard in many industries. Grounding is an effective way to mitigate this hazard. Grounding provides a path for static electricity to safely discharge to ground. Grounding is also important for controlling electromagnetic interference, or EMI. EMI can disrupt the operation of electronic equipment. Grounding can help to reduce EMI. Grounding is a versatile technique that can be used to improve electrical safety and performance. The effectiveness of a grounding system depends on several factors. These factors include the soil resistivity, the type of grounding electrode, and the size of the grounding wire. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for a grounding system. The type of grounding electrode also affects the effectiveness of the grounding system. Common types of grounding electrodes include ground rods, ground plates, and ground grids. The size of the grounding wire is also important. The grounding wire must be large enough to carry the fault current. The grounding system should be designed to minimize the impedance to ground. Impedance is the opposition to the flow of alternating current. Low impedance is desirable for a grounding system. The grounding system should also be designed to provide a low resistance path to ground. Resistance is the opposition to the flow of direct current. Low resistance is desirable for a grounding system. The grounding system should be connected to the earth. This connection provides a path for fault current to flow back to the source. The grounding system should be installed in accordance with the NEC. The NEC provides specific requirements for grounding systems. The grounding system should be inspected and tested regularly. This will help to ensure that the grounding system is working properly. Grounding is an important part of electrical safety. By following safe grounding practices, we can all help to prevent electrical accidents. The grounding system is a critical safety feature in any electrical system. It provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock and damage. A properly designed and installed grounding system can prevent electrical hazards. These hazards include electrical shock, fire, and equipment damage. The grounding system should be designed to minimize the impedance to ground. Low impedance is desirable because it allows fault current to flow quickly back to the source. The grounding system should also be designed to provide a low resistance path to ground. Low resistance is desirable because it reduces the voltage drop across the grounding system. The grounding system should be connected to the earth. This connection provides a path for fault current to flow back to the source. The grounding system should be installed in accordance with the NEC. The NEC provides specific requirements for grounding systems. The grounding system should be inspected and tested regularly. This will help to ensure that the grounding system is working properly. Grounding is an important part of electrical safety. By following safe grounding practices, we can all help to prevent electrical accidents. NEC Table 250.122 provides guidance on sizing equipment grounding conductors. Proper sizing of the grounding conductor is essential for safety.